NENOMATICA, where mathematics meets YouTube excellence. Welcome to our mathematics video. Today, we'll be solving a challenging algebraic proof problem, following a specific algorithm to verify the equivalence of expressions. Let's look at our example problem. We need to prove that the expression x plus 3 times x plus 4 times x plus 5 times x plus 6 minus x squared plus 9x squared minus 360 equals 38x squared plus 342x. Let's solve this step by step following the algorithm shown. First, we'll rearrange the left side of the equation. We'll group the first four terms, x plus 3, x plus 4, x plus 5, and x plus 6. We can rewrite this as x plus 3, x plus 6, x plus 4, x plus 5, minus x squared plus 9x squared minus 360. Now, we'll apply the common term identity. This identity states that a plus b c equals a squared plus a times b plus c times c. Using this identity, we can expand our group terms. For the first group, x plus 3, x plus 6, we have a equals x, b equals 3, and c equals 6. This gives us x squared plus x times 3 plus 6 plus 3 times 6, which simplifies to x squared plus 9x plus 18. Similarly, for the second group, x plus 4, x plus 5, we have a equals x, b equals 4, and c equals 5. This gives us x squared plus 9x plus 20. Now, let's rewrite our expansion in a more useful form. We can express the first part as x squared plus 9x plus 18 times x squared plus 9x plus 20. Let's now identify the common term. We can rewrite this as x squared plus 9x plus 18 times x squared plus 9x plus 20. This helps us see the common factor more clearly. Once again, we'll apply the common term identity. If we let it equal x squared plus 9x, b equal 18, and c equal 20, we can use the formula. A plus c equals a squared plus a times b times c. Applying this identity, we get x squared plus 9x squared plus x squared plus 9x times 18 plus 20 plus 18 times 20 minus x squared plus 9x squared minus 360, which simplifies to x squared plus 9x squared plus x squared plus 9x times 38 plus 360 minus x squared plus 9x squared minus 360. Now, we'll simplify by canceling the common terms. The x squared plus 9x squared terms cancel each other out. Also, 360 minus 360 equals 0. This leaves us with just x squared plus 9x times 38 distributing. We get 38 times x squared plus 38 times 9x, which equals 38x squared plus 342x. Welcome to our lesson on expanding triple binomials. Today we'll learn how to multiply expressions in the form of x plus a times x plus b times x plus c. Let's start by examining the general formula. For any real numbers x, a, b, and c, we'll see how to expand the product of three binomials. Now, let's prove this formula step by step. We'll work through the expansion carefully to see how we arrive at this result. We start with the expression x plus a times x plus b times x plus c. First, let's multiply the first two terms, x plus a times x plus b. Using the distributive property, we get x squared plus a plus b times x plus ab. Next, we multiply this result by the third term, x plus c. We'll distribute the multiplication across all terms in our first result. Now, we need to combine like terms. Let's group all the terms with x cubed, then x squared, then x, and finally the constant term. And there we have our result. We've expanded the triple binomial product into a polynomial with four terms x cubed, a term with x squared, a term with x, and a constant term. Let's apply this formula to a specific example. We'll expand the expression x plus 2 times x plus 3 times x minus 4. First, we identify our values. Here, a equals 2, b equals 3, and c equals negative 4. Now we can substitute these values into our formula. Let's simplify. The coefficient of x squared is 2 plus 3 minus 4, which equals 1. The coefficient of x is 6 minus 8 minus 12, which equals negative 14. The constant term is 2 times 3 times negative 4, which equals negative 24. Let's try another example with a slightly different form. This time, we'll expand 2x minus 1 times 2x minus 3 times 2x plus 5. For this example, we need to adjust our approach slightly. We can factor out the coefficient 2 from each x term, or we can directly apply the distributive property. Let's factor it to get 8x cubed times the product of x minus 1 half times x minus 3 halves times x plus 5 halves. However, it's more straightforward to apply our formula directly. We first need to rewrite our expression in the form required by our formula. We can write it as 2x minus 1 times 2x minus 3 times 2x plus 5. For this to match our formula pattern, x plus a, x plus b, x plus c, we'll need to factor out the coefficients of x. Let's rewrite it as 2 times x minus 1 half times 2 times x minus 3 halves times 2 times x plus 5 halves. Now we can apply our formula with a equals negative 1 half, b equals negative 3 halves, and c equals 5 halves. Let's simplify. The sum of the coefficients is negative 1 half minus 3 halves plus 5 halves, which equals positive 1 half. For the coefficient of x, we have negative 1 half times negative 3 halves, which is 3 quarters, plus negative 1 half times 5 halves, which is negative 5 fourths, plus negative 3 halves times 5 halves, which is negative 15 fourths. Adding these, we get 3 quarters minus 5 fourths minus 15 fourths, which equals negative 17 fourths. The constant term is negative 1 half times negative 3 halves times 5 halves, which equals 15 eighths. Let's summarize what we've learned. When expanding a triple binomial in the form x plus a, x plus b, x plus c, we get 4 terms. First, x cubed. Second, the sum of a, b, and c multiplied by x squared. Third, the sum of the products of AC and BC multiplied by x. And fourth, the product ABC as our constant term. This pattern makes it much easier to expand these types of expressions without having to multiply everything out each time. Welcome to our math video. Today, we'll be working through an algebraic proof that shows how to expand the product of 4 binomials. Let's start with our problem statement. For all real numbers x, a, b, c, and d, we need to prove that the expansion of the product of these 4 binomials, x plus a times x plus b times x plus c times x plus d, is equal to x to the 4th power plus the sum of a, b, c, and d times x cubed plus the sum of all possible products of 2 variables times x squared, plus the sum of all possible products of 3 variables times x, plus the product of all 4 variables a, b, c, and d. Now let's begin our proof. We'll expand this step by step. First, let's rewrite the product by grouping the first 2 binomials and the last 2 binomials. Now let's expand the first group, x plus a times x plus b. Using the distributive property, we get x squared plus a plus b times x plus a times b. Similarly, we expand the second group, x plus c times x plus d. Again, using the distributive property, we get x squared plus c plus d times x plus c times d. Now, we multiply these 2 expanded expressions. We use the distributive property to multiply each term in the first bracket by each term in the second bracket. Let's rearrange the terms by grouping the like powers of x. We have x to the 4th power plus terms with x cubed, which are c plus d times x cubed, and a plus b times x cubed plus terms with x squared, which are cd times x squared, a plus b times c plus d times x squared, and ab times x squared, plus terms with x to the 1st power, which are a plus b times c times d times x, and a times b times c plus d times x. And finally, the constant term a times b times c times d. Now, let's simplify the coefficients. For the x cubed term, we have c plus d plus a plus b, which equals a plus b plus c plus d. For the x squared term, we expand a plus b times c plus d to get a times c plus a times d plus b times c plus b times d. So the coefficient becomes cd plus ac plus ad plus bc plus bd plus ab, which we can rearrange as ab plus ac plus ad plus bc plus bd plus cd. For the x term, we expand a plus b times c times d to get a times c times d plus b times c times d, and a times b times c plus d to get a times b times c plus a times b times d. This gives us acd plus bcd plus abc plus abd, which we can rearrange as abc plus abd plus a CD plus BCD. And thus, we have proven that the expansion of x plus a times x plus b times x plus c times x plus d equals x to the fourth power plus the sum of a, b, c, and d times x cubed plus the sum of all possible products of two variables times x squared plus the sum of all possible products of three variables times x plus the product of all four variables a, b, c, and d. This is exactly the form that we wanted to prove. Welcome to our math video on finding the value of function f of 0 in a polynomial. In this video, we'll learn how to find the constant term in a polynomial using the relationship between the coefficients of a polynomial and its value at 0. Let's first understand what f of 0 means in a polynomial. Consider a general polynomial function f of x. When we substitute x equals 0 into this polynomial, we get the constant term, which is the coefficient that doesn't involve any x terms. Now, let's look at the method that we'll use to find f of 0. According to the hint in our problem, the sum of the coefficients of x terms in a polynomial f of x equals f of 1 minus f of 0. Let's solve an example together. We want to find f of 0 by using the relationship between f of 1 and f of 0. Let's rearrange our formula to isolate f of 0. We know that the sum of coefficients of x terms equals f of 1 minus f of 0. Let's rearrange to get f of 0 on one side. Thinking phase quick challenge. Can you think of how to find the sum of the coefficients of x terms? Pause button, take a moment to think about it. Let's understand what the sum of coefficients of x terms means. In a polynomial, f of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub 1 times x plus a sub 0. The coefficients of x terms are all coefficients except a sub 0, which is the constant term. Let's figure out how to calculate the sum of these coefficients. We can evaluate the polynomial at x equals 1 to help us find this sum. When we substitute x equals 1 into the polynomial, each x term becomes 1, so we get f of 1 equals a sub n times 1 to the power of n plus a sub n minus 1 times 1 to the power of n minus 1 plus a sub 1 times 1 plus a sub 0. Since any number raised to any power of 1 is just 1, this simplifies to f of 1 equals a sub n plus a sub n minus 1 plus a sub 1 plus a sub 0. Now we can find f of 0 using our relationship. We know that f of 1 equals the sum of all coefficients, including a sub 0. And we also know that f of 1 minus f of 0 equals the sum of coefficients of x terms, which is all coefficients except a sub 0. So f of 1 minus f of 0 equals a sub n plus a sub n minus 1 plus a sub 1. Also, f of 1 equals a sub n plus a sub n minus 1 plus a sub 1 plus a sub 0. If we subtract the first equation from the second, we get f of 1 minus f of 1 minus f of 0 equals a sub 0. Simplifying, we get f of 0 equals a sub 0. Let's visualize this concept with a diagram. In a polynomial, each term has an x component and a coefficient. When we evaluate at x equals 0, all terms with x vanish, leaving only the constant term a sub 0. When we evaluate at x equals 1, all x terms become 1, so we get the sum of all coefficients. The difference between these two evaluations gives us the sum of coefficients of only the x terms. Let's summarize what we've learned. 1. F of 0 in a polynomial is equal to the constant term a sub 0. 2. The sum of coefficients of x terms equals f of 1 minus f of 0. 3. We can rearrange this to find f of 0 equals f of 1 minus the sum of coefficients of x terms. 4. Through algebraic manipulation, we proved that f of 0 equals a sub 0, confirming our understanding of the constant term in a polynomial. Today we're going to solve an interesting algebra problem that involves finding the coefficient of x to the power of 99 in a large product expression. Let's start with the problem. We are given the expression x plus 1 times x plus 2 times x plus 100. We need to find the coefficient of x to the power of 99 in the expanded form of this product. This product consists of 100 binomial terms, starting from x plus 1 and ending with x plus 100. To solve this problem, we need to use an important rule from algebra, the generalization of the common term union. This rule helps us expand products like this. When we expand this product, we'll get terms with different powers of x, from x to the power of 100 down to the constant term. We need to identify the coefficient of x to the power of 99. According to the algorithm shown in the image, we can expand the product using the generalization of the common term union. The expanded form will look like x plus 1, x plus 2, x plus 100 equals x to the power of 100 plus 1 plus 2 plus 100 times x to the power of 99 plus 1 times 2 times 100. We can see that the coefficient of x to the power of 99 is the sum of all the constants in our binomials, 1 plus 2 plus 100. Now, let's calculate the coefficient of x to the power of 99. We need to find the sum, 1 plus 2 plus 100. We can use the arithmetic sequence sum formula, n times first term plus last term divided by 2. In our case, n equals 100, the first term is 1, and the last term is 100. So the sum equals 100 times 1 plus 100 divided by 2, which equals 50/50. Looking at the approach shown in the image, we can see that it confirms our calculation. The sum of the first 100 natural numbers equals 100 divided by 2 times 1 plus 100, which equals 50/50. Therefore, the coefficient of x to the power of 99 in the expanded form of x plus 1, x plus 2, x plus 100 is 50/50. Let's find in the expanded form of x plus 1, x plus 2, x plus 100 is 50/50. Let's consider the following expression, x plus 1 times x plus 2 times x plus 100. Our goal is to find the sum of all coefficients when this expression is expanded. To solve this problem, we'll use a clever approach involving a substitution. Let's define a function f of x that represents our expression. Let's see what happens when we substitute x equals 1 into our function. When x equals 1, we get f of 1 equals 1 plus 1 times 1 plus 2 times 1 plus 100, which simplifies to 2 times 3 times 101, which is equal to 101 factorial divided by 1. When we expand our original expression, we get a polynomial in x. Let's write it in the form a sub nx to the power of n plus a sub n minus 1x to the power of n minus 1 plus a sub 1x plus a sub 0, where n equals 100, since we're multiplying 100 terms, each with the highest power of x being 1. Now, let's see what happens when we substitute x equals 0 into our function. When x equals 0, we get f of 0 equals 0 plus 1 times 0 plus 2 times 0 plus 100, which equals 1 times 2 times 100, which is 100 factorial. Now, the key insight, the sum of all coefficients can be found by evaluating f of 1. When we substitute x equals 1 into our expanded polynomial, each term contributes its coefficient to the sum, because x to any power equals 1 when x equals 1. Following the algorithm shown in our problem, we'll calculate f1 minus f0. We have f1 equals 101 factorial, and f0 equals 100 factorial. So f1 minus f0 equals 101 factorial minus 100 factorial. Now we can factor out 100 factorial from this expression. We get 101 factorial minus 100 factorial equals 101 times 100 factorial minus 100 factorial. We can factor out 100 factorial from this expression. We get 100 factorial times 101 minus 1, which simplifies to 100 factorial times 100. Now, we've reached our final answer. The sum of all coefficients in the expanded form of x plus 1 times x plus 2 times x plus 100 is 100 factorial times 100. Let's understand why this approach works. The difference f1 minus f0 gives us the sum of all coefficients of terms containing x non-constant terms. Since f0 equals a sub 0, the constant term, and f1 equals the sum of all coefficients, their difference represents the sum of all non-constant term coefficients. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.